Hello everyone, I'm Aditya Raj Agarwal and this presentation is a part of completion of my course Cryptography in college. So the topic of the presentation is blockchain and security. Blockchain, as most of you will be knowing most of you will be knowing is a new concept, relatively new concept, which is booming in the technology industry right now, with many applications in a lot of places and with one of the most revolutionizing invention of money transaction, the Bitcoin. So, uh, in this presentation, I'll first brief about what a blockchain is and how it works. And in the later part, we'll be discussing about the security properties and the possible attacks on it. For for the beginning, while I describe blockchain, I will be rushing through most of it because the main topic is about security of blockchain. But if anyone wants to understand the topic in much more detail, at the end of the video, I'll cover one example, one very small blockchain which I created, which I coded in C++. So what a blockchain is? A blockchain is blockchain. The concept of blockchain is that if I have to describe it in one line, it will be that it is a list of nodes where each and every node is dependent on the node preceding it. Now, these nodes are stored distributed across all the users in the network. That is why it gets the it it gets distributed, like the force point distributed comes from that. A ledger of all transactions, that is because that all the transactions which are ever made are recorded, like all the nodes which I just referred, which are actually called blocks, are stored across the network. Then the basic concepts again are like it's a ledger, there's hashing used, there's cryptography used, and finally it is distributed using a tough mess problem. These will be covered in the next slides in depth. So, being a public ledger, that the first and the foremost important point is that all the transactions from the time of creation are stored in this public ledger. This helps in a lot of points as we'll see in security properties later on, like traceability. Then each node can be accessed by all trans each node. Yeah, each node as in like each node here means a user. Every user can access all the transactions in the network. Then for building these, for making a block, for counting a block, so basically I said that there are lists of nodes. These nodes are blocks, and this list is chain because every block is dependent on the previous block. It gets the form. It gets the name of a chain. So for adding a new block, miners are required, which are basically high-powered computer systems, which have to do some computationally hard problem to get the privileges of adding a new block. Then, as it is mentioned in the next line, so hash-based keys. Hashing is the Hashing gives the immutability to blockchain. By immutability, we mean that once something is written, it cannot be modified. So, because let's say the block number 5, which is dependent on block number 4, and which is succeeded by block number 6, if anyone wants to modify this block number 5 for their own personal benefit, which is probably something which should not be done, like double spending or something. So if anyone wants to edit block number 5, and if even if they do, then that will change the hash value of block number 6. And since it is distributed across the whole world, across the whole network, one change will be people will get to know that there has been a change and that block number 5 has been tampered with. So hash gives the immutability to it. Then these keys, like every block which is a collection of transactions, that block is dependent on that block is the that block is associated with the key. Again, this will be very well illustrated in the example blockchain which I have built, which I will explain in the last of the at the end of this video. So each block has a lot of transaction fields. Other than that, there's a field of previous hash value, which is the hash value of the previous block, and it has its own hash value, which is calculated based on the previous hash value and the transactions inside the present block. Okay, so change in this point I've already described, and yeah, all transactions, the way like I described how transactions, like how keys work, that way all transactions have their own keys, which are dependent on the previous transactions, previous blocks. Now, cryptographic hashing and challenge. So one of the most important, like, okay, first of all, cryptography is used to provide confidentiality and everything that uh, sender and the receiver, all of them are not revealed directly, so you can maintain your anonymity. But other than that, one of the major uses of cryptography is it comes into mining. As you'll see in the next slide, as you'll see in the next slide, mining requires solving a tough problem, computationally tough, and the solution is based on cryptography methods. Again, like I'll be rushing through it because I have to cover properties and security later in the video. So, going briefly to the points, when a new block is to be added, a challenge is associated, which I said proof of work. Then the solution and the challenge together should give an output. The output has a particular number of zeros in prefix. This particular point is basically taken from the Bitcoin blockchain. Bitcoin, as we all know, is the most predominant, is the predominant form of blockchain being used in the market right now, in the world right now. Also, these IDs which are associated with every transaction are, like as we see in the first slide, all have their own transaction IDs. So these are also cryptographically made. This is again, this is just for maintaining the confidentiality. This is not very important though. Then, okay. So now we come to what all applications are there already in place. Cryptocurrency, as I've mentioned multiple times in the video already, that cryptocurrency is the most used application of blockchain right now. And in that also Bitcoin is the single most predominant cryptocurrency used. So a blockchain is a shared public ledger on which the entire Bitcoin network relies. So this network is basically that all the Bitcoin blockchain, as we call it, the blockchain which is just some strings in some order is visible to everyone in the network. You can go on bitcoin.org or like any other website and you can access the Bitcoin blockchain. All confirmed transactions are included in the blockchain. The integrity and chronological order of the blockchain are enforced with cryptography. Chronological order, as in again the immutability thing, that if block 5 has to come before block 6, it cannot. It has to come before block 6. It cannot come in any other order because that will change the hash values. Now, Bitcoin has a lot of scope, and like in all these fields, work has already been going on. Like banking, Citibank, and Axis Bank, and everyone, they are coming up with their own blockchains to maintain their records basically. Because record keeping takes up a lot of revenues of the bank, so they are keeping blockchain to having a decentralized record keeping mechanism. In cybersecurity, again, by cybersecurity, we mean that the underlying blockchain, if it is secure, then the whole system becomes secure. So, let's say right now, if there's some application which doesn't use blockchain, and we can replace, like let us say that we can replace that already implemented method by using blockchain. So we'll implement blockchain, and as we because we know blockchain is safe, and as it will be discussed further in the video. As we know, blockchain is safe, then that implementation will be safe. Supply chain management. Supply chain management is deals with the supply chain of, let's say, agricultural products from the very start, from the very plantation of seed to the manufacturing of wheat flour from it. A lot of steps come in the middle. So all these steps right now are hard to keep, and there are proper firms for that. If you create a blockchain, we can track a single grain of wheat from the very start to the very end. Then comes networking and IoT. So, as mentioned in the report alongside the presentation, IoT IoT can rely on blockchain to a great extent uh, because as we know, wireless network is a little less safer than the wired network. So, to be ensured that the communication, the signals which are coming to the cloud are from a genuine source, we can use blockchain because we can track where exactly did the record come from because that is visible to every other device and to the cloud, like to the basic one central unit. Share market, yeah, because of the distributed nature of blockchain, it does away with the need of brokers. Now we'll move on to the security aspect of it. So in security, in cybersecurity, there are basically three, and like we call confidentiality, integrity, and availability as CIA of security. One more important aspect is non-repudiation. So these four properties combined can are basically important for any system to be secure. Firstly, I'll describe all these properties in brief. Confidentiality is basically data secrecy. Let's say if I have some data, I want that no one else can see it. If I'm transferring some data from if a sender is transferring some data to the receiver, that sender won't will like that the any person who's trying to who intercepts the data in middle should not be able to gather any information from it because it might be confidential data. So that's what confidentiality means. Integrity. Integrity is basically if integrity is basically when a sender is sending some data to receiver. Let's say there's a there's a there's a there's an adversary who intercepts the data and changes it and then sends it to receiver. The receiver should know that the data is not authentic, that the data is not sent by the actual sender. That is integrity. That is communication integrity. Another form of integrity is process integrity, where if I am processing a data, when I'm processing a data, that time while the data is being processed, no one should be able to modify the data. Like while I am having the data, no one else could corrupt the data. Availability, as it is written, this is the definition by National Institute of Standards and Technology, ensuring timely and reliable access to and use of information. Yeah, to user. My mistake. There should be to user. So availability is basically, let's say if I'm an authenticated user in a network, then I should get the access to the network. As simple as that. Like this is quite intuitive. That if I'm an authenticated user, should get access. On this, there are few attacks called denial of service attacks, another form of attacks, where they flood the network, making it unusable by the actual authenticated users. Then comes non-repudiation. Non-repudiation means that if I have given, if I like, if there's a sender and there's a receiver, and some transaction has taken place between them, then neither the sender nor the receiver should be able to say that they did not make they did not make the transaction. Basically, they should not be able to repudiate. This can create problems like, um, let's say I'm selling selling a piece of land to someone. The buyer gives me the money, then I claim that I did not say that I'll sell you the house, or maybe I claim that I claim that I did not do that. So I get the money and I do not even sell the house. So this becomes a problem. Now, in the next few slides, we'll be discussing each of these properties one by one. Like each of these properties one by one, as in with regards to blockchain, how the concept of blockchain helps to deal with all these. Confidentiality. So blockchain in a blockchain, the blockchain network can be of multiple two types broadly. Firstly, is a public blockchain network, which is like an example of which is a current day used cryptocurrencies like Bitcoin, where anyone can access any transaction that has ever happened on the network. Then there are private blockchains, which is basically like an industry, like an organization built a blockchain for itself. Here, only authenticated users get access to the blockchain. Now, once an adversary has entered the blockchain network, be it public or private, both are same. So for the 3 points, we'll be discussing as only the a blockchain, not public blockchain or private. So to maintain confidentiality, because let us assume that an adversary has already entered the system, okay, and can intercept the data. Like, let's say there's no need of intercepting first of all, because the adversary, if having the access, will be a node in the blockchain network and will get all the data. But in that case also, the, that adversary should not be, maybe it's a requirement that that adversary should not be able to see the data, infer anything from the data. So here comes the importance of end-to-end encryption. These are the current day communication protocols, that data has to be encrypted end to end, which means that if there's a sender P and there's a receiver Q, so the data which P sends to Q, even if it is seen by R, then R should not be able to infer anything from that. P uses his own P uses a public key, and Q uses its own private key. That way, if anyone uses Q uses the prescribed private key to encrypt to decrypt the data. This way, even if someone who is not expected to see the data, will not be able to. If anyone is not expected to see the data, he or she will not be able to. These keys have to be strong. So basically, an adversary should not be able to put an attack on the key and infer, like, get the key. So for these, strong algorithms are used, which are usually these days big integer problems like um, D-log or elliptic curve problems, which are NP complete. So one of the basic key exchange mechanisms are RSA these days, and it uses the concept of large primes and the fact that we cannot infer that we cannot infer the values P and Q from it. Yeah. Next, the identity of parties remain encrypted. So confidentiality for some might mean that, okay, people should be able to see that. For example, in Bitcoin, a person should be allowed to see that, yeah, this much Bitcoin was transferred, but a person might not want his or her name to be let out. That way, if the identity of the parties is maintained, is encrypted, then a person might be able to see their usernames, but that person will not be able to actually know the actual identities, real world IDs of those people. Next comes the property of integrity. So here basically there are two very important properties which blockchain provides us with. Immutability, as we already discussed, is refers to not being able to delete a transactions once it has been done. Traceability means that if a transaction is done, I should be able to track the original own. Let's say if 10 bitcoins are transferred from one place to another, and then to some other place, and then to some other place. Or let us take the example of supply chain management. That a kilogram of wheat is transferred from the farmer to some middleman, and then finally to the floor maker. Then we should be able to trace the original owner. So these two properties are very important, and I'll explain how these are provided by blockchain. So first of all, immutability. Immutability is provided by Immutability is provided by hashing all the blocks and connecting and making the hashes dependent on the previous hash uh, of the dependent on hash of the previous block. So if any previous block is tampered with, its hash values get changed, and because of the dependency, the succeeding block's hash value gets changed, and hence the hash values of each and every block after that gets changed. So this maintains immutability. As if I'm changing something, if I'm, let's say, if I'm a user, I'm changing one block, I need to change all the blocks succeeding that, and that becomes computationally hard. As we'll discuss, there's an attack called majority attack, where people try to get majority into their favor and change all the blocks. Traceability is maintained because it's a distributed network. A person cannot, like a source, cannot get lost in that. As and when these two properties are provided, there obviously comes a risk. Let's say if I'm a user and I want that all my data is gone, how do I maintain that? How to have the right to being forgotten? So to deal with this, we can have all the we can have mechanisms to encrypt the identities such that if once the keys are forgotten, there's no way that the actual traceability can be attained. Again, these 2 points, traceability and right to be forgotten, go against each other, but then that comes to the developer of the application as to what is more important. Next, availability. So a basic attack on availability is the DDoS attack. Okay, and it seems very easy to implement a DDoS attack on blockchain. DDoS attack is basically where they use distributed denial of service. Like a lot of computers attack. Like here I've explained the DDoS attack. Yeah, I've mentioned the DDoS attack. A lot of computers flood the network with fake requests, and as such, when an actual request comes, the network is already busy. So it seems very easy to implement it because all the nodes are already on the network, and you are a node on the network and you just have to throw requests. But it is not very easy because of the following 2 points. So there's no single point of failure. Okay, there's operational resilience. I'll first describe what is operational resilience. Operational resilience is basically that there are multiple nodes. So if um, an attacker attacks one of the nodes and destroys it, basically in terms that makes it unusable by actual requests, then that node can be just dropped and the work will still go on because nodes are used for storage of the distributed network data, and that data is obviously present on multiple other nodes. So dropping one node will not cause much harm. Similar to that, there's no single point of failure. So um, let's say basically there's no single point of failure in terms that if a node is being attacked, like if an attacker is attacking nodes, that attacker cannot attack all the nodes present in the network. There has to be a limit, and when that limit is attained, like let's say those number of nodes are unusable right now. We're not throwing them out just in like operational resilience. We're just ignoring them for a while till the time the attacker is busy with them. We are using the other nodes. In operational resilience, we are using exploiting the fact that there are multiple users. There are like a lot of users, and we can basically be okay with losing out on one of the nodes. Then comes non-repetition. So again, traceability and immutability are the keys of providing non-repetition. Non-repetition, as I explained earlier, stops with like is important to stop double spending. Like let's say I'm a user. I'm using Bitcoin. I purchased something using Bitcoin. Gave I gave the seller. I sent the seller Bitcoins, and then I say that I did not send the Bitcoins and I still have them. Then I can use those Bitcoins again in some transaction. That should not be allowed. So non-repetition deals with that. The two important, I've already described what traceability and immutability are. So because of traceability, a person can trace the source of the thing in demand. Let us again use the example of wheat flour. I'm a middleman. Let's say I'm the final flour manufacturer, wheat flour manufacturer. I can claim that I never got the flour when I actually did. In such a case, the traceability will come into factoring that, yeah, where did the floor go? If it did not come to me, then whom did it go to? And because everyone has it, like the data is distributed through the network. one can trace it back to me. Immutability, let's say in non-repudiation, let's say I did, yeah, in double spending, let's say I gave the money to the seller and then I later claim that I did not give, so I'll have to remove that block. I cannot remove that block. I cannot edit that block because of immutability. Next, we'll discuss the major attacks on the blockchain. Here, I like to first start with the majority attack, which is which I have kind of explained in the slides preceding this. So majority attack is basically when an attacker gets hold of more than 50% of the mining nodes. Mining, if I get hold of more than 50% of the mining nodes, I can use them to modify the blocks according to my need. Let's say if I have to modify a block, if I have to modify a block, that block once modified will change the hash values of the next block. And since the main blockchain is the one which is the longest, if I have more than 50% of the mining nodes, I can just create more blocks with correct hash values. And actually, I don't need to create more blocks with that correct hash values. Majority attacks, if a new block has to be added to the network, it is done in a way that one of the miners come up with a solution, and more than 50% of the other miners have to say that more than 50% of all the miners have to say that yeah, this proof is correct. So I'll come up with a like the attacker will come up with a random solution, and because he owns more than 50% of the miners, they'll all say yes, the solution is correct. So within fraction of seconds, he can add a new block. So let's say there are 10 blocks. I modify the fifth block. That block once modified, I can make sixth, seventh, eighth, ninth, 10th, and 11th block, hence making the new fork the main chain. Okay, so like I've made the new fork the main chain, and the previous chain has just 10 blocks. This one has 11. So this will become the longest chain. So by having majority of the miners, I can do that. Next is the Sybil attack. Sybil attack is when you own most of the nodes. So basically, all the data which is distributed on the network. So with data, again, the same thing happens that if many users have the data, many nodes have the data, then the correct data is assumed to be the one which most of the nodes carry. So let's say if the attacker owns more than 50% of the nodes, he can keep fake data on the nodes, and that will be believed to be correct. So if I'm the attacker, I'll keep random data. I'll keep all the data which I want. So anyone accessing the blockchain will be given the data which I want them to receive. Hence, I can create anything which I want. I can give myself all of the bitcoins there are. I can give myself. I can do whatever I want with the blockchain basically. Next is the DDoS attack, which we discussed in availability. DDoS attack, as we described then, is when a lot of computers flood the network with fake requests, hence not allowing actual requests to be passed. So this is dealt again, like as we discussed in availability. This is dealt by because of no single point of failure and because of how courtesy of operational resilience. After all this comes the implementation errors. Like as we discussed that majority attacks, Sybil attacks, DDoS attacks, these all can be easily dealt with. Like DDoS attack, we saw how it can be dealt with. Sybil attack and majority attack can be dealt by not allowing bots on the network using capture, by not allowing monopoly on the network, by keeping the terms and conditions like that, by checking if a particular user is owning most of the mines or owns most of the nodes. So these can be taken care of by the implementation. But then there are some implementation errors which are pure foolishness. So let's say if there's some error in the code written, like there was one error in the Ethereum blockchain there was once an error because of which in the Ethereum blockchain there was once an error, and because all of these are open source network, everyone had the access to the code on GitHub. So one of the attackers saw the glitch in the code and exploited it and extracted something like $100,000 worth of cryptocurrency. Then there are hardware implementation issues that you know that your system cannot handle a particular number of requests, again coming to the DDoS attack, and you don't have so many nodes that you can do away with a few nodes. So yeah, if you are not implementing the blockchain, it will obviously create error. So in conclusion, I like to say that blockchain is a very secure technology. The problem comes only during implementation issues, like the ones which I described. Again, I like to focus on confidentiality, integrity, and availability, how the blockchain deals with them, and because these are the major security properties. Now, if you, so the presentation is now over basically, and if you are a user who wants to understand more of blockchain, I'll continue with an implementation of the blockchain which I coded in C++. Okay, so I'll start with that. So this has been coded in C++ uh, and the editor which I'm using is Sublime Text. So here I'm defining a block. This block is basically this block contains a sender, this a receiver, value. Then there is a previous hash, current hash, and timestamp. These are the six fields which are in the block. Out of yeah, so these are the six fields in the block. This is the constructor function. This is a generate hash function, and these are the accessors to the all the values: sender, receiver, value, previous hash, current hash, time. The constructor function just assign the generate hash function. For now, generate hash function, I've used a pseudo, not a very strong hash. Like I've created a random hash. This is like a standard, some values basically. And this is obviously not the way to implement it. In actuality, we use SHA 256 or um, Blake or some other strong hashing mechanism. The construct I used it just because I wanted it to be a little easy to implement. Like, uh, yeah, because it is just an illustration. I'm not using it commercially. I can do with having it a little less secure. The constructor function just assigns the values which it gets. Like when a new block will be created, these values will be assigned. And here there's a point to note that every block every block contains just one transaction. In actual Bitcoin or any other cryptocurrency, this is not how things work. Again, this is just for illustration. So we are keeping it a little simple. Now, coming to our main function, we have to have a genesis block because because we need a previous hash value. So because Genesis block is the block which is the first block which is created in the blockchain. We hard code it with some fixed values. These values which I've written for now as 0, 0, 0, 0. These will be fixed and these will be known to the public. That yeah, this is a Genesis block. I've I've uh, I've created a Genesis block, and in the constructor function, the generate hash function is called by itself. So I'm sending the value of the sender, which is a string, receiver, which is a string. The value is in terms of the transaction values, and previous hash. I'm sending it 0 because let's say I'm keeping it the standard. Now this line is just to print out the hash value which is generated, which is 2304 in all the cases, and like in the case of Genesis block. So I create a vector for the chain. Chain is the list, as I've said. I create a vector for that vector of blocks, and I push the first Genesis block onto it. Now, now this is going to be my input file t0.txt input file, and t1.txt is going to be my output file. The input is going to be taken in a format like input is going to be taken in a format that it will be it will name of the sender one, receiver one, value 1, then sender 2, and so on. This is the format of our t1.txt file, t0.txt file. Now, I'm sending this to reading input and writing output are two of my functions. Where in reading input, I take the input from the t0.txt file and uh, keep it. Basically, I keep it in the blockchain in the vector which I've created. I'm passing it as a parameter. In the writing output, I write the output on t1.txt. So reading input. This is a basic file opening thing. Here, using simple loops and if conditions, getting the I'm getting the information. I'm getting the first three lines. Let's say in this line, I got sender one, sender one here. In this line, I retrieve sender receiver one in the first iteration. In this line, I receive value one. Okay. Uh, I keep all these values in variables for now. Then this is just for debugging. I was using this a lot of couts during debugging. I create a new block with the values which I took from took just from the file, like took from the file just now. Okay. Chain dot back dot get hash gives me the previous hash value. So hash of the previous block is attained directly from the chain. We are not feeding it manually. Now, when a new block is created, I just push that block onto the end of the chain, being the newest block. I do it again, like I do it as many, using the while loop, I do it again and again. And once it is done, I just close the file. And yeah, this is basic error correction. If this there's some error, it will just say that file opening error. It is in against this error. While writing output, I'll while writing output, I'm opening the file. I'm just iterating. I'm having an iterator on the of the chain, and I'm just writing the hash values out of the chain. That's pretty much that's pretty much it. So I have the input in a file. This is the input. Basically, these are uh, next. I'll open it in Sublime Text. Yeah. So this is the input. Sender one, receiver one, value. Sender receiver value. Sender receiver value. So yeah, when I run it, it will create a file called t1.txt. Actually, I'll for running it, I'll have I usually do it on Ubuntu, and I'm currently using Windows, so I'll have to do it on code blocks, which might take a couple of minutes to start because I don't usually use it. Sorry. So once I use it, it will create a new file by the name t1.txt, which will have our uh, required blocks. So sorry for the wait, but yeah, it will. The only part which is left now is to show how values are stored. So these in this code, I'm just storing the hash values as I have written here. Only the five values which are going into the file are only the hash values. This helps in a way to maintain confidentiality because you can just keep the values of the hash. You can just keep hash and do not store the um, senders and receiver the parties basically. And to check for immutability, you still have the hash values, and you can like basically simulate the actual transactions and check it against the hash values which are there in the file t1.txt. So yeah, this is open. I'll run it, and I'm getting an error. So let us just put it to be uh, 0 for now because we are not using timestamp anyways. Now, as we see, we got a t1.txt t1.txt file as the output. Let's just open it. Let's just open it on Sublime. And this is the Genesis block. This is block 1, which was taken from these three values, the hash of that. This is block 2, taken from these values, and similarly. So I'll illustrate what will happen if I change just a small thing. If I make it from 10, I make it 11, the first block. From my guess, from my guess and from how it should be, these all these will be changed. So let us run the code now. Let us go back and check the t1.txt file now. So previously, cancel. I'm not loading it again. Previously the values were these. Now if I put the new txt file, it's not here. Yeah, if I open it in Notepad itself, the values are totally different. We can see. So even a small change results in such a big change. This is the basic concept of blockchain. Thank you. This will be it for the video.